let's get into derivation of first law of thermodynamics. Prior to that, it's very much essential for us to understand sign convention that we use. Now this is the system. Now if work is done on the system, it's positive. If heat is provided to the system, it is positive. But if system does work on surrounding, then it is assumed to be negative. And if it is supplying heat to the surrounding, then also it is assumed to be negative. Fine. With these sign conventions, let us proceed towards derivation of first law of thermodynamics. Now this is the system. As I told you, every system has internal energy U1. So suppose this is n moles of gas over here, which has internal energy U1. Now to that system is provided heat. So it becomes U1 plus Q positive because provided to system. Then work done on the system plus W. So it gets to U1 plus Q plus W. So U1 plus Q plus W is what is final internal energy. So U2 is equal to this thing. So I take U1 this side. So it gets U2 minus U1, which is del U. So we get an equation for del U, which is Q plus W, right? So we get into this equation, which we have got to keep in mind. Now, we also know W when we do over here external, we are bothered about external pressure. So it becomes minus P del V. So W gets the value of minus P del V. So del U is equal to Q minus P del V. Now, if we intend to get the equation in terms of P del V, then if I take this over here, it becomes del U plus P del V is equal to Q. Fine. So these are the equations. These are the two equations in terms of work and in terms of P del V. Alright. So these are the equations that we derived, and this is what is first law of thermodynamics. Now let us apply it to isothermal process. Now we already have done isothermal process. In isothermal process, we saw how surrounding takes care of heat. Whenever in the system temperature rises, surrounding takes care of it. It takes away the excess of temperature, and whenever the temperature falls, surrounding provides the heat required. Surrounding provides the desired heat required and brings back the temperature to what it was initially, and we saw that right in our earlier videos. And we also found that del T is equal to 0, temperature is maintained. Del U, since del U is function of temperature, so del U is also 0. Q, since there is exchange of it, so Q is not equal to 0, and del H is also not equal to 0 since Q is being exchanged. Fine. So here let's get back the equation. Del U is equal to Q plus W. Now here del U is 0, so we are concerned with this. So what we do is we substitute here 0. Q is equal, so 0 is equal to Q plus W. So W is equal to minus Q becomes the equation for first law of thermodynamics in isothermal process. What's the fate in terms of adiabatic process? Let's understand. Now del U, same equation. In adiabatic, we saw that del T is not equal to 0, del U not equal to 0. Why? Because vacuum, no surrounding taken care of temperature. So temperature rises or falls, whatever, depending upon exothermicity or endothermicity. Fine. So del T not equal to 0, del U not equal to 0, but Q is equal to 0 because there is no exchange of heat in between the vacuum and the system. So Q is equal to 0. Since Q is equal to 0, no exchange of Q, so del H is also equal to 0. But here in this equation, we are concerned with Q. So Q is equal to 0, so W is equal to del U. That's the fate for adiabatic process. Now what happens to isochoric process? In case of isochoric process, we know that del V is equal to 0. Iso, same volume, so V2 minus V1 is equal to 0. So obviously W minus P del V, that also becomes 0. So obviously here del V is 0, so W gets 0. So del U is equal to Q. That's about isochoric process. Now what happens to isobaric? Isobaric is constant pressure. Pressure is existing. We are not, in our formula we don't have del P, we have P. So pressure exists. So the equation remains as it is. So it's only in isobaric process that the equation remains as it is, otherwise it all gets modified in all other processes. Okay, so this is what is first law of thermodynamics, sign convention and values the equation as derived for varieties of processes. Keep these things in mind, keep these things in mind well. Okay.